Hey, Physics 20s, Mr. Jukley here, getting ready to teach you a little bit about Newton's second law of motion. Now, I made a couple mistakes on this sheet already. In the past, I've had it as two classes, so that's why it's labeled as class 1. Forgot to get rid of that. We're actually going to do the whole thing right now. We're just going to do a bit of a shorter version. And then the other piece of this, like you know, we're focusing on the essentials for the next level, right? So essentials for Physics 30. So big things that you need to know about this one, like really big things, is you need to know Newton's second law. So you need to have the idea of second law in one dimension is sort of the big thing that you need to know. And also you need to be able to relate to our kinematics unit. So those are the really big things. You're going to notice, and what I'm going to call this is I'm going to call it enrichment, if I could spell. Enrichment, it's Newton's second law in 2D. Now, that being said, 2D stuff is very important. Like you need to know how to add by components, solve things using those ideas of components and using vector addition triangles and stuff. That being said, this particular part of 2D stuff, less so. So I hope that makes sense. If you have questions, obviously just send me an email or over Google Classroom is great. But we're going to focus for the most part on these just second law in one dimension and also relating to kinematics. Okay, so let's jump into it. Newton's second law. Big idea is if you have unbalanced forces, it's going to accelerate in the same direction as the net external force. So it's just our definition that we've got up here. In other words, the net force, the sum of all the forces, when you add everything up, it's what you got left over. It's going to be the exact same direction as the acceleration. So if this is the only force acting on this vehicle, it's going to accelerate in the same direction. If this is the only force acting on this thing, it's going to accelerate in the same direction. We can also look at this in terms of a bit of a formula, and we'll just do that somewhere. Let me find some space on the board here. In terms of a formula, we look at it, F net is mass times acceleration, and we'll explore this a little bit more, but it's saying whatever's happening to my net force, well, we've got a direct relationship with my acceleration. So if acceleration is in the positive direction, my net force is in the positive direction as well. Because remember, these are indeed scalars, so that's the only place where you'd see direction, because mass does not have direction. You can't have a negative mass in terms of direction or just amount or anything, realistically. So in the same direction is sort of the key. So just kind of thinking about this real quick here. And one thing to really note is that squared is very important. When people are new to this, they often confuse like 4 meters per second with 4 meters per second squared. They're not at all the same thing, right? One's for velocity. This one is a velocity or speed, whereas the one that we're actually dealing with in this problem, 4 meters per second squared, is an acceleration. So if I look at these two forces, this is kind of an improper force diagram, but I've got an applied force and a force of friction. Those are the two forces that are acting on this crate in the horizontal component. If I know that my acceleration is towards the left, that means I know that my net force must be towards the left. And if my net force is towards the left, how do those two forces, my applied force and my force of friction, relate? If you're thinking to yourself, the applied force needs to be bigger, so the applied force needs to be bigger than the force of friction, you're absolutely correct. Because when we add them up, we need more going towards the right than towards the left. So I'm going to do this using a diagram and make it maybe a little bit more to scale. So I've got my applied force going towards the right. I've got my force of friction going towards the left. And then my resultant, which I'll do in red here, is my net force. It's got to be going towards the right, the same direction as my acceleration. So hopefully that makes sense to people. It is a kind of an important little piece here. So whatever the direction the acceleration is, that's the direction of the net force, and you need more force in that direction, or bigger forces in that direction. So again, our equation for this, Fnet is mass times acceleration. Let's start to explore that one a little bit more. First and foremost, you already know the units for net force, right? So we know that net force is a Newton. But if we wanted to figure out alternative units for this, we have to look into, well, what is mass, right? So net force is newtons. Well, mass is kilograms. And what is acceleration? Acceleration is meters per second squared. So I say 1 Newton is equal to 1 kilogram meters per second squared, or times meter per second squared. Perfect. So we should, and we will see, and messing around with these units is kind of an important piece for us in Physics 20, and we often see that in Physics 30 as well. What are equivalent units for this, or equivalent units for that? So this is, I think, our first look at that. Our first look at equivalent units, and we'll be dealing with that more. What I like to do for this is just plug the units in where the formula would be, and then we can rearrange from solve from there. Cool. So if I'm thinking about the acceleration, and I'm thinking about how much acceleration we have, it depends on two things. So first thing that I'm going to do is I'm going to rearrange my equation so that I've got acceleration is equal to everything else. So acceleration is going to be net force divided by mass. And we can go through and we can now start to think about, okay, well, if the acceleration depends on two things, we can clearly see it's the net force and the mass. So if I wanted to do a little experiment here, right? So manipulated, responding, and controlled variables, I might do an experiment where I'm exploring what happens when I change the net force and what happens to the acceleration, right? So we're changing the net force. Net force is going to be our manipulated variable. And then what happens to the acceleration? The acceleration would be my responding variable. And then a very, very important thing for a controlled variable would be the mass. So the thing that we really want to look at for this is we're going to look at the relationship between the two. So what I'm going to say is I'm going to say acceleration is proportional to the net force. So it's not equal to, but it's proportional to. So we're taking out of the formula everything that's not going to change, everything that is a controlled variable, not going to change. Mass is going to be consistent. And I can almost treat this, again, I'm not saying that acceleration is equal to net force. I'm just now looking at how it's related to net force. So this is actually a direct relationship. And I can treat a direct relationship, or I can treat this relationship kind of like I treat a formula. So if I were to multiply this side of a formula by 2, what do we have to do to the other side? Multiply by 2. So there's our direct relationship. If I multiply the acceleration by 2, the net force gets multiplied by 2 as well. So again, that's called a direct relationship. And if I wanted to graph that, right, if I wanted to graph to show what would happen, we got to remember that our manipulated variable always goes on the x-axis. So in this case, our manipulated variable would be net force, and our responding variable always goes on the y-axis, so acceleration on the y-axis. And if it is indeed a direct relationship, it should be a nice, neat line. So we double the acceleration, we double the net force. I said that a little bit backwards. We triple the net force, we triple the acceleration, and so on and so on. So just kind of the idea of this, and when we put the little cartoons in, it starts to make a lot more sense. So if I've got one sled dog that can pull with a force of 100 newtons. So that's all that that dog can do. That's its absolute maximum force. And it's pulling on a 50 kilogram boulder for some reason. It might have an acceleration of 2 meters per second squared. Nice. If I double the amount of dogs, so I've now got 2 dogs that can each pull with 100 newtons, I'm going to have a force of 200 newtons acting on that same mass. So there's my controlled variable, and we're going to double the acceleration. So we double the force, we double the acceleration. Cool, not so bad. Not so bad. The other thing that it depends on is mass. So I'm just going to rewrite this. Acceleration is net force divided by mass. Now, if I wanted to look at the proportionality for this one, I'd say, okay, well, acceleration is proportional to, so I'm getting rid of net force. Mass is still in the denominator, right? So I should probably have a placeholder in that numerator. I'm going to put a 1 up there. This is now an inverse relationship. relationship. And if we think about it in terms of an experiment, well, now we are changing the mass, so that is our manipulated variable. Our responding variable, we're still looking at what happens to acceleration, and our controlled variable, the thing that we're forgetting about, the thing they're saying we are not going to change, is our net force. So again, let's check out this inverse relationship a little bit here. Remember, we're treating this proportionality kind of like an equation. So let's say that I doubled the mass. So I multiply the mass by 2. Now forget about what I did to the mass. Let's just think about what I did to that side of the equation. We just put a 2 on the bottom or the denominator of that side of the equation. So in other words, we've divided that side of the equation by 2. If I want to keep things equal, I have to divide the other side of the equation, or in this case, I guess, proportionality by 2 as well. So when mass is doubled, acceleration is multiplied by 1/2. And what happens as we go through this, let's say mass is triple, acceleration is divided by 3. Mass is multiplied by 100, acceleration is divided by 100. So as the mass increases, the acceleration decreases. The shape of the graph is going to look, I'm going to do better than that. The shape of the graph is going to look something like this. So again, as mass increases, the acceleration decreases. So let's check out another cartoon. This is a bit of a ridiculous one, but it works. So we got a golfer. Golfer is hitting a golf ball, pretty usual so far, so not so bad. The golfer can only apply so much force on that golf ball. So the force is just the force that the golfer can apply. The golf ball has a very, very small mass. A very small mass is going to lead to a very big acceleration. So that when that person hits that golf ball, it's going to go flying and it's going to get going very, very, very quickly. That being said, the golfer might for some reason be swinging at the back of a truck. I think that's what this one is showing us here. A golfer hitting a truck with a golf club. So we've changed here. The force is still exactly the same, but now we've got an extremely large mass, and as we increase the mass, we decrease the acceleration. Again, that's that inverse relationship. You do the opposite things. So when you decrease the mass, you increase the acceleration. When you increase the mass, you decrease the acceleration. Again, keeping it so that our net force is constant. Cool, so not so bad. So we get a couple examples with this here. Well, one example with this in particular. We've got the acceleration of an object is 24 meters per second. If the net force is tripled and the mass is doubled, what is the new acceleration? So let's go through and we'll start with our original formula. And I like to write this out just like we would write out a normal form, but I like to leave a little bit of space. So acceleration is net force over mass. Awesome. So it's saying, let's see here, if the new net force is tripled, that means I need to multiply the net force by 3. I just multiplied this side of the equation by 3 or put a 3 in denominator. I need to do the exact same thing to the other side. Cool. So if the net force is tripled, the acceleration is tripled. Then let's see here, it says the mass is doubled. So I'm going to multiply the mass by 2, but then I realized, well, I actually just divided that side of the equation by 2 or put a 2 in the denominator. I need to do the exact same thing over on this side. So my new acceleration then is going to be 3 over 2 times my old acceleration. So I'm going to say my acceleration, I'm just going to call it my new one for some simple labeling, is going to be equal to 3 over 2 times my old acceleration, which is 3 over 2 times, what was it there? 24. I'm getting lazy here, not putting units in. Let's fix that. Being lazy never helped anybody out. 24 meters per second squared. So get out your calculators, plug that one in, and hopefully we end up with 36 meters per second squared. Cool, so not so bad. Big thing is just treat it like an equation. What you do to one side of the equation, you do the exact same thing to the other side of the equation. Nice. Let's check out the next little piece here. So this one is now really coming together with some of those big ideas of net force and also this Newton's second law with net force is mass times acceleration. So let's go through. You got a 15 kilogram block. That's cool. We know that's a mass. It's pushed to the right with a force of 48 newtons. Awesome. So let's see. Let's maybe call that, because it's actually being pushed with that, let's call that our applied force. Our applied force. So 48 newtons towards the right. It says its acceleration is 1.8 meters per second towards the left. So that's my acceleration. And we want to determine the second force, which, well, let's just call it F2. Could be a friction force, could be who knows what, but it's F2 is what we'll call it for now. Nice. So one of the things that I really like to do with this takes us back to lesson 1 actually, and it is drawing a free body diagram, getting our bearings around us and figuring out exactly what's going on. So it's a block. I'm going to make a block square. Very nice. And our force diagrams or free body diagrams, we know only external forces go on them. So the only external force that we're really given is the fact that we have our applied force 48 newtons towards the right. Now, I'm not yet going to call that positive or negative or anything because I got the arrow showing my direction. Cool, so that's not too bad. It says its acceleration is 1.8 towards the left. That doesn't actually go on a free body diagram, so I'm just going to put it off the side. Acceleration is 1.8 meters per second squared and towards the left. So if the acceleration is towards the left, what does that mean in terms of our net force? Also got to be towards the left. So F net has to be towards the left. And then what does that tell me about that second force? So if overall my net force is towards the left, that second force has to be 1 towards the left, and it has to be bigger than my applied force. So I'm going to make this just so it's super, super, super clear that it is indeed bigger. Cool. So this is pretty much everything we've got. Now, everything in this unit from here on in is going to come down to 2 things. Net force is mass times acceleration, and net force is the sum of all forces, which in this case is our applied force plus our force, what did we call it? Force 2 in this case. Let me clean that up a tiny little bit. Force 2. There we go. So always, always, always comes down to those 2 things. Like pretty much everything in this unit from here on in. Those 2 formulas are beyond important. So let's go ahead and let's think about this a little bit. So F2 is what we're looking for. It's going to be equal to my net force minus my applied force when I rearrange it. Now you notice that I haven't thought about directions here anywhere yet. So what I want to do is maybe just set up a little thing, and let's set up, let's say right is positive. Usually is, so keep with the usual. Cool. So this is now going to allow me to figure out my second force. So my net force, if I expand on that a little bit, well, it's just mass times acceleration. And my applied force, well, that's just my applied force. I have the number for it. So now I think we've got every single little piece that we need to solve for F2. We know the mass, we know the acceleration, we know the applied force. Let's just pay really close attention to directions. So the mass, what was the mass here? A 15 kilogram block times the acceleration. So the acceleration was, let's see, 1.8 meters per second squared, but it's towards the left. So we'll be very, 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 I'm even gonna like put a little arrow next to it in a different color because it's so important that we're including the directions. Let's go back to, is that the right color? Okay, good stuff. And then minus my applied force. My applied force was 48 newtons towards the right. So minus 48 newtons. Now it doesn't really look like these units are working out, like you're subtracting weird units from newtons, but remember kilograms meters per second is the exact same, is the exact same thing as newtons. Lost my train of thought there. So take a moment to plug the numbers in. Put it on pause if you need to, but take a moment to plug the numbers in. I end up with, I believe, negative 75 newtons when all is said and done. So yes, negative 75 newtons is F2. I just put the video on pause for myself and double check that. One thing to kind of note here is we said, well, if right is positive, what is negative? So we might also want to put this back into terms of the original question. So 75 newtons left would be a good answer for that as well. So not so bad, not so bad at all, right? It's again, it's a look back at that idea of what net force is, the sum of all the forces, but then adding in this idea net force is no longer zero, net force is something like a non-zero number. Directions, again, quite important. So I don't think you have an example for this one, but I do want to just show you this really quickly. It's a ton of review. It's the idea of kinematics, and we remember kinematics, and well, dynamics is what we're talking about right now. So kinematics, if we're dealing with uniform motion, we know the only formula that we can really use is V is equal to D over T. That is our uniform motion kinematics formula. What about forces when we have uniform motion? Well, forces, if it's uniform motion, I know my net force is equal to 0. So all of those pieces fit in well together. That is one of the really extremely big ideas. The other part of this is, well, what if I don't have uniform motion, right? So for accelerated motion, and I'm just doing this off to the side over here, we know that F net is mass times acceleration, and we know that it's not equal to 0, right? So not equal to 0. And then we know that we can make this variable list, so like VI, VF, A, D, T, and am I missing anything from there? I don't think I am. So make a variable list, and then use that variable list to pick a formula and solve. Perfect. So with all of these questions that are combining kinematics and dynamics, the first thing I would think about, is it uniform motion or is it accelerated motion? Very first thing to think about. The second thing I'd think about once I figure out if it's uniform or accelerated is I'm either going to use my idea of forces, so my dynamics idea, to figure something out about the acceleration, and we're typically going to be looking at the accelerated motion part. So can I use my forces to figure out the acceleration and then use that acceleration in my kinematics, or can I use my kinematics to figure out my acceleration and then use that in my forces, my dynamics? So let's just check out this first one real quick here. 5,000 kilogram car traveling forward at 31 meters per second. So this is some sort of speed. As its brakes applied, the resistive force is 8.7 kilonewtons, so I'm going to call that a force of friction. Determine the time it takes for us to come to rest. So we're not even going to solve this one. We're just going to come up with a plan. So our overall goal is time. Is it accelerated motion? Absolutely, because it's starting at 31, so we can change that to VI, and then it's coming to rest. What does rest tell us about speed? If it's coming to rest, it's VF, and if it's at rest, it's 0. So let's see, we've got VI, we've got VF, let's see, and I think that's all the information that's really given to us in terms of kinematics, but we are looking for time. If we had acceleration, could we solve for time? Absolutely, and you can look at your data sheet, you can pick out a formula that would work for that, but we don't have acceleration. So then the other piece that we need to look at is, well, we know the net force is mass times acceleration, and we know that the net force is going to be equal to the sum of all forces. So that's going to be our forward force, or our applied force, plus our force of friction, keeping in mind that our force of friction is going to be opposite, so don't forget about the direction there. So, and actually, sorry, I think I missed one thing here. If the brakes are slammed on, is there a forward force? Is there an applied force, like when you're braking your car? Not a significant one, actually. So the net force in this case, I think, is actually just going to be equal to our force of friction. So if I know my net force, or sorry, if I know my force of friction, and I know my net force, I'm just going to rewrite that one more time. It's kind of a mess right now. F net is equal to force of friction. If I know my force of friction, and I know that my net force is mass times acceleration, we can find the acceleration, and then I can use that acceleration to solve for my time. Perfect. That's not too bad, I hope. Right? And it's a bit of a mess, and we're not actually solving things, but it's things that we've done before. Right? So first find the acceleration, right? And here's sort of the idea for this, knowing that F net again is equal to, oh, they called it a resistive force. I'm just going to change that to a force of friction there. So we solve for acceleration, and then we take a look and we pick an appropriate formula and we solve for our time. Perfect, not so bad. So at this point, that's sort of the need to know. That is the essential everything that we've talked about so far. I'm going to keep going a little bit here. If you want to hang out and you want to talk about the 2D stuff, that's okay. I'm just going to roll through it really quickly. I think most of it's typed out for me anyways. But if you want to roll through 2D stuff, awesome. Good stuff. If you are putting the brakes on here, no pun intended from the last example, practice for this, like really good practice for the 1D, is essentially questions 1 to 10, and then what was I calling it there? Enrichment. If you want to check out a couple enrichment questions, 11 plus 12 are the way to go. Perfect. So if that's it, if you're good to go with the 1D stuff and you're feeling like that's enough for the time being, we'll see you again soon. If not, just hang tight and we'll have a look. So this one is not in our workbook for the people moving forward. This is just an activity, something to think about. So if we wanted to go through and think about, okay, well, first off, could I sketch the vector sum diagram for this? It's kind of already like it's in components, right? So we'd add up all of our x's, we'd add up all of our y's, and then we could make a new right angle triangle and solve, right? And if we know the direction of the net force, we know the direction of the acceleration. So let's just have a quick look at this, like a real quick look at this. So in my x's, if I was looking for the net force in the x component, well, that's going to be 800 newtons, so positive 800 newtons, plus negative 500 newtons. So that's nice easy math, actually. I really like that. That's 300 newtons towards the right. That's not bad. My net force in the y component, right? Well, all I've really got in the y component is F4 and F3, so that's 200 newtons plus negative 600 newtons. Well, that's going to be negative 400 newtons. Now, if I have F net in the x and I have F net in the y, and I wanted to put those two things together to get my overall net force, let's see, I would have x net x, and that's 300 newtons towards the right. I'd have F net y, a little bit bigger. F net y is 400 newtons downwards. Notice we ditched the negative there because now it's all in our diagram in 2 dimensions. I'd have my overall net force going down at an angle like this. So the question is, could you solve for that net force using some Pythagorean theorem? Could you solve for the angle using some tan function? And yes, absolutely you can. You can do that. We've done that a whole bunch before. Perfect. Now, if I know that the net force is at that angle going downwards, so F net is at whatever angle this is, Newton's second law says whatever the direction the net force is in, that's going to be the exact same direction as my acceleration. So my acceleration is going to be in the exact same direction. Right? Well, that's messy. Exact same direction. So to figure out the direction, well, we can look back at our net force. To figure out the magnitude, we still just know F net is equal to mass times acceleration, so we can absolutely go ahead and solve for acceleration. No problem. Cool. So same ideas, just in 2 dimensions. So this is just a little bit nicer with some actual answers, but yeah, we could definitely do that. Good. Actually, I'll go a little bit slower, give you opportunity to read this. If you need to put it on pause to take a bit more time, that's cool, go for it. Next one, same idea. If you need to put this on pause to take a second to read it, it's pretty much everything we just talked about, just typed out a little bit nicer. Cool. The last example that we've got here, and this one again, this is sort of the extension or the enrichment piece. It is a big old 2D question. So here's the key with this though. The acceleration is 35 meters per second squared towards the west. So the acceleration is towards the west and it's 35 meters per second squared. We want to determine the F2 and we want to determine the angle for F2. So that's all this stuff down here. So the big key is I'm doing the whole thing in components. So I can think about my net force. Actually, let's go back one little split second there. Just a split second there. What is my x component of my acceleration? Well, if it's towards the west, all of it's x, so all of it is my x component. So that means that my net force in the x component is just the mass times the acceleration in my x component, which is the entire 35 meters per second squared. Cool. What about the y component? An acceleration in the y component. Well, if all of it is x, that means none of it is y. And if I have 0 acceleration in the y, well then what's my net force in the y? 0. There's absolutely none. So that's sort of the key. We've got accelerated motion in the horizontal, and we've got unbalanced forces horizontally, but we've got balanced forces vertically. So my net force vertically has to be equal to 0. So as I go through and as I kind of check this out, again, first step with anything is to, with any of these components problems, is to break them all into x and y components. Cool, so we see that done up here. That's no problem. If we wanted to analyze those y components, let's see. I'm just going to put the video on pause actually for a second to save you a bit of time. All right, back at it here. So essentially what we've done is we've said, like we said in the last slide, I get a different color to highlight here, Fnet is equal to 0 in the y component, Fnet in the y component is equal to F1 plus F2. So what that really means is F1y must be the exact same thing as F2y because they have to cancel each other out perfectly. You can actually see that on the diagram over here nicely, but in the opposite direction. So if F1y worked out when we did the math and did 150 times sine of 25 was 63.39 in the positive direction, or up, F2y must be 63.39 downwards. Nice. We can do the exact same thing for the x component. Again, I'm just going to put it on pause here to save you a bit of time. So you'll see all the writing show up in a second, but bear with. All right, cool. So just got this in the x component kind of solved for us. So things that I start with, Fnet in the x is equal to F1x plus F2x plus F3x. I rearranged and solved for F2x. So Fnet minus F1 minus F3, all in the x component. Then I start to expand on what we've seen here. So I know that my net force is mass times acceleration. I know that F1 in the x component, from the diagram over here, we're dealing with cosine. And I know that F3 in the x component, well, that's just F3. There's really nothing else there. It's all x component. So we plug in the numbers, and we're very, very, very specifically paying attention to all these directions here. So what should be in the positive direction, what should be in the negative direction, and then we plug in the numbers, and turns out F2 is 14.05 newtons in the negative direction, or 14.05 towards the left. And that makes sense because we need bigger towards the left, bigger forces towards the left than we need towards the right. Cool. So last couple steps here already done for me, which is nice. Now if I want to solve for the unknown force for F2, I just use Pythagorean theorem to figure out the magnitude, and I can use tan function. This is written a little bit funny. It'd actually be theta is inverse tangent of 63.39 over 14.05 to get the angle. So remember, when we're looking for the angle, we use the inverse, and then we would probably say something like, well, I mean, it's labeled clearly on the diagram, but we could say something that, let's see, south of west, if we wanted to be very specific for that one. Cool. So for those of you who hung out for the extension, awesome. Thanks for spending a bit more time with me. That is it for now. Make sure you're working on the practice. Remember that number 11 and 12 are indeed extensions. And yeah, talk to you again real soon. Bye for now, Physics 20s.